All right, so in this question, we are told there's two students determine the speed the ball is released. So we're looking for V0. Thrown vertically upward in the air, throws the ball into the air while the students measure the total time the ball is in the air. Students use a meter stick to measure the release height of the ball. So with the situation where the ball is thrown upward, the meter stick measures the release height. So this is the Z0. The ball goes upward, and the time can be used to measure the entire time, the entire delta t, upward and downward. So in some ways, this is very much like the lab we did with the Free Fall 5 in class, where we can know the total time in the air that the ball had until it comes back down. We're being asked to know which equations could use to determine the speed the ball was released. So So let's take a look at our relationships first. V equals AT plus V0. Now, so we're going to do some thinking beforehand. Now, if we use this, when this is the instantaneous velocity, the acceleration is g minus 10, and that total time in the air we could measure, plus V0. So we're looking for V0, and we're looking for that. So if we knew, the only velocity we know is that we know that this initial launch velocity, V0, will be equal to V when it gets to the end point. But it'll be equal and opposite to each other at the end point, at some moment in time. This V over here will equal that V0 when it returns exactly to that exact same height. So that's an important thing to know. If we look at the other equation we have, z equals 1/2 AT squared plus V0t plus Z0. Well, we're given our initial height here. We are looking for this. We know our acceleration, and we will know our time. So like the other equation, we will know z and Z0 if it returns to the same height. And we know the acceleration, we have the time. So again, we will know z and Z0 if they're the same height. This z and this Z0 are the same, just as V0 and V will be the same. So these two will be the same, and these two will be the same, allowing us to get this. The real problem is that if we know the time, to get this V0, we need to know this final velocity. So these two will be equal to each other, but they have to know what they are. And we don't know which one either is. Over here, for the position equation, we know the acceleration, we know the time, we're going to measure it, and we know the z and Z0 because we're getting back to the original height, which means we will know everything except the V0. So, use this equation from the moment in time the ball is released to the moment in time it reaches its highest point, up to here. Now, that's not what we just described before. The problem is they describe using the meter stick to determine Z0. It doesn't say they use it to determine the Z up here. So we're skeptical of this one because we'll know Z0, but we don't have a way to get Z for sure. They're calling it Y. But if that were the case, it would work. Now this next one says from the moment in time which the ball was released to the moment in time which the ball hits the ground. Well, hitting the ground is like this. Now, what will be true is we will know this Z, and we will still know that Z0. Since we're using the meter stick to measure the height from the ground, we will know the height here, and we will know the height here. So, whereas we didn't know this Z value at the top, we will know this Z value at the bottom. So it looks like this is a better answer than A. And now here, we're asked for number C. From the moment in time the ball was released, so that is some V0, which is what we're looking for, to the moment in time which the ball reaches its highest point. Its highest point is up here. Now we will know the acceleration, but since the meter stick is only being used to measure the initial position, knowing this additional height up here isn't something we're guaranteed. So the weakness we have here is the same weakness we have here. there's some ambiguity in the design, so we clearly know we'll have what we need with B. And then we run into the same problem with D, irrespective of what it says, because we don't really know that Y. So C and D are out for some ambiguity. A is out because of some ambiguity about whether we can get that Y, but clearly we have everything we need for B, and that's why it's choice 6. All right, so we have an object thrown near the surface of the Earth. Of course, these assumptions about air resistance and gravitational field constant are standard. It's thrown upward vertically with a velocity v. We know at the top it's v0 is some number, and at the top the velocity would be equal to 0. We know the acceleration is the same everywhere, g everywhere. The direction and magnitude of the acceleration in the air is the acceleration is never upward, because the acceleration is caused by gravity, and that's the Earth and the person attracting each other. So that acceleration for the person is always going to be downward, so it can't possibly be upward. And it's not decreasing, it's always 10. It's not increasing, it's always 10. It's constant. Number 8, a kitten sits in a basket near the edge of a table, kicks the basket off the table. So when we look at this, we've got our categories. We've got the basket and we've got the kitten inside, like so. Someone kicks it, like so, to go off. So, oh, this is a horizontal projectile situation. That helps us to recognize that. All right, so the cat comes out of the basket, and for some time when they're in the air, the cat and the basket are separated from each other. But what we know is the basket and the cat both had an initial vertical velocity of 0. So that means they're both in free fall. They will both hit the ground at the same time, no matter what happens. All right, so if the air resistance is negligible, what's the acceleration of the kitten basket system? Well, again, so if these two things get separated, then what we have is we have the kitten and the basket separated from each other, but it's the center of mass that's accelerating toward the Earth. It's the center of mass that's accelerating toward the Earth, and they will both hit at the same time. So we do know the acceleration is directed downward. Acceleration fluctuates, false. The acceleration cannot be determined, false. So we're left at choices A and B, and that magnitude is equal to g because the system is the projectile. Again, we take the cat and the basket and consider the center of mass, and it's the center of mass that's going to move along that parabolic trajectory.